Alright, we're almost ready. Just need to finish fixing something on my end. Just get all my reference code up, and then we should be all good. Give me 2 seconds. Well, hello everyone and welcome back to OpenGL. Hope you're all doing well. This is probably maybe one of the more climactic streams, on par with the octree stuff, because today we're going to be looking at shadows, which is pretty big. But I just need to finish this shit. 1 sec. This is highly unprofessional. Okay, give me 2 seconds. You guys can watch the train ride as I get ready. Alright, almost there. And then last file to open. Alright, now I got everything up. Okay, let's get started finally. Alright, I'm gonna do that. And we should be all good. Alright, Alright, so like I said, we're going to be doing some shadows today. And we'll be first going over the concepts, and then we will implement the code only for directional light today. And we'll see why, but it'll be the simplest to explain and then the easiest introduction into the topic. Okay, so for shadows, let's first recall what directional lights are. So this is good. Alright. Yeah, so directional lights is like a sun, and it's like super far away. All the light rays are parallel because it's so far away, so we can just assume that they're all parallel. Oops. Like that. And the one relation that we want to take out of this is that if we have an origin, so the 0 vector, the direction is going to be in relation to the negative of the position. Because when we look at directional lights, or lights in general with shadows, we're going to have to, the way we're going to do it is we're going to render the scene from the light's perspective. So we have to have some sort of position for the light. And for directional lights, it turns out that since all these rays are parallel, the direction is in relation to is anti-parallel to the position vector. So this is one of the direction vectors, and these are all the same direction vectors. And then the position vector, we have some constant that relates them, and it's going to be the direction is equal to some negative, I'll call it K P. So if we use a direction vector here in a directional light, it turns out that we don't need to pass in a position anymore, and we can take it right from here, because essentially it will always be looking at the origin. If we look at our world, the sun is so far away that our little tiny world, if we consider our world the center of the earth, the 0 vector, all these light rays are parallel. So, and this position is going to be looking at essentially the 0 vector of the earth. So that's the directional light, and that's how we're going to be looking at directional light today. But for shadows, now this is going to be more about shadows. I should have talked about shadows first, but that's directional lights. And now for shadows, essentially what we're going to look at is the way we're going to render shadows is we have to find out what the light can see. So it's almost as if we're going to have a camera on the light, but we don't want to have a camera on the light, where instead we can just, it'll be like we're, it's going to be a little weird to explain, but instead of having a camera on the light, we're going to use the camera's value, so its position and direction, which in the directional light's case are related, so we only need one. They will be, we will use the position to kind of create a camera, not using the camera class, but something of the sort. So let's say that we had, I'm going to draw another directional light here, and let's say we had an object, two objects. One right here, this is a box, and then we have a floor. And directional light goes like this. And let's say the origin was over here. Do I want to put the origin over here? It doesn't really matter, but I'll put it right over here. So that's our origin, and let's say our view, our camera, so the user camera, is right here and it's looking down. Or like that. And we want to render this fragment at point P. But with shadows, what happens is this box will be blocking the light. So we want to find a way to know that, and what it's gonna, the way we're gonna do it is we're gonna take the directional light, and we're gonna render the scene from the directional lights, and then if the point, and then that's the first pass, and then in the second pass, we'll render the scene again from the camera here. And then from the camera, we'll see, is this position, is it in the light's fragment buffer or frame buffer? So we'll have an FBO for each of the lights, and if this position is inside of the FBO, if it's not blocked, then we will render it as if the light was shining on it. Otherwise, we'll render it as just being a shadow. So that's how that's going to work. I realize now that was a shitty explanation, but I will definitely put a link to the Learn OpenGL article, because it's very quite extensive and is very good at explaining it. It's essentially this, but I didn't know how to explain it, so but the way we're gonna kind of figure all this math out is, let's go back to the concepts of transforming stuff. So let's say that this point, let's say we're on the floor here, and relative to the center of the box, or of the floor, this point P has some value here. Now, if we want to transform it to the origin, to the world space, we're going to need a model matrix. So let's say this is the origin. So I'm going to call this vector here P, which is the position in the model. And then this is going to be the world's position, where that's just the position of the object of the fragment in the world space. That's going to be transformed using the model matrix, if you recall what that is. And then to get it into our view, we had to multiply it by a projection and a view matrix, which were specific to the camera. Now we're going to do essentially the exact same thing. We're going to generate matrices for the directional light. They're going to be different types of matrices and different projections, but it'll be essentially the same gist. So yeah, we're gonna have kind of a specific projection and view for each viewer of the world, and we already have one in our camera, which is get the projection matrix. We have a function there, and then we also have, then we're going to have update matrices for the sun or the directional light, and then in the spotlights and point lights later on. So that's the whole gist of shadows. Alright, so let's get into Visual Studio, and then we can start writing some code. Ooh, what just happened? Alright, in Visual Studio, we're first going to do a little bit of cleanup here. In assets, I just want to kind of organize this stuff. So let me see how I have this. Alright, I'm going to create 2 new folders, one called textures, and that's where we're going to put some textures. I'm just organizing the assets folder right now. And then another folder called shaders. And then we're going to put all our shaders in here. That includes putting the instanced folder in there, and then all of the shader files in there. And because of this, we're going to have to update the paths in main.cpp. So main.cpp, you can, just going to delete some stuff here. You can just add the extra path. So it's assets / instance. That should become assets / shaders / instanced. Just change all these here. Perfect. And then the other thing I noticed when I was going through this was in mesh, when we render the stuff and we set shader.setInt no text to 1, we actually have to set that to 0 if there are no textures. So just in the else, so in mesh.render here, in the else block, just put shader.setInt no text 0. Because if we're using the same shader for for rendering 2 different objects, one that has material and one that has textures, it will carry over the value, since we don't re-render or update the shader in between rendering objects. Okay, so that's pretty much a little bit of cleanup, and now let's do some things here. So, like I said, we're gonna have a different FBO for each directional light. In our case, we're only gonna have one because we have one directional light, and we only are gonna care about the depth value, not the colors, because we only care about how far an object away is from the sun, from the light source. And that's how we're going to determine if something is in the shadow. We see here the point P is further away than the box to the sun. So therefore it will be in the shadow because the depth value of the point is greater than the depth value of the box in the sun's perspective. And of course they're on the same trajectory line. And because they're all parallel, we can actually use an orthographic projection, which is pretty cool. And we'll get more into that later. Let me actually just close all these. Okay, so we need to do something in frame memory.hpp. We need to add 2 new methods here to the frame buffer object. And the reason why is because if we only care about the depth buffer, we don't want to waste any memory on saving colors. And this is pretty synonymous to what we did with the depth.fs. When we were rendering to the depth shader last video with the classes, we just assigned it a white color because we didn't really care about the other calculations with lights and shit, because that wouldn't show up in the depth buffer. But there's also a way to just disable that altogether, and that's just saying void, or it's going to be a GL method called GL draw buffer, and we just set it to GL none. So we're going to have two new methods in the frame buffer class. One will be void disable draw buffer. You know, we can actually just say disable color buffer. And then we can just, and then in here we need to make two calls: GL draw buffer, and pass in GL none, and GL read buffer, pass in GL none. So this will just allow us to bypass writing to a color buffer, which will save a lot of memory on the GPU. Okay, now for some of the light stuff here. We're going to go into light.h here. Light.h, not h. Okay. Like I said, we're going to only be worrying about directional lights, but a lot of this stuff will transfer over to point lights and spotlights, just with a few different rendering methods, because just of how these translate over to cameras. Like with the directional light, all the light rays are parallel, so we're going to use an orthographic projection. With a spotlight, it will only point light onto one single plane, so it'll be similar to a directional light. However, we're going to need to use a perspective projection, because it has a cone of view, just like our camera. But with a point light, it turns out we're going to use a cube map once again, because it radiates light in all directions, which is pretty cool. That'll be the next few videos in this. I'll probably have one video, or I mean, I think the spotlights would be pretty easy to implement after this, but I'll see how long it takes, and then I'll decide how many videos to do with it. Okay, so in directional light, we're gonna have to add a few things here. We'll add some variables or fields first. The first one is going to be a bounding region. This bounding region will tell, or it will define the region in which we want to define shadows. And that's relative to the direction and the position of the light. So if you can think about, let me actually just open up Paint 3D here. Is there 3D view? Here we go. How do I remove the canvas? Show canvas now. Alright, so if we have our sun, that's right here. How do I rotate? Alright, let's just say our sun is right here. And then we have a direction, and I don't know if there's a 3D arrow. Is there a 3D arrow? Nope. Here, I'll just use a cylinder. There we go. Alright, so let's say this was our direction. Oh, that looks like, it looks like fucking, what does that look like? I don't know, whatever. Oh shit, what does it look like? Looks like, is it Bionicles? Might be Bionicles. Well, let's say this is our sun, and their direction is this thing on this cylinder that's pointing out here. What was I getting? What the? Oh yeah, the box. And we want to define shadows for a certain area here. Because if we define it because for the projection matrix, we're going to need some sort of face or plane to present it on. And it's going to be like, it's going to look like this, where we want to render shadows within this box here, only within this box. And in video games, typically, you'll have that this box is dependent on where the player is. So if the player's out here, we'll move it out here. And it will be the same because the projection matrix is orthographic. We don't care about the cone of view. It just sheds parallel light everywhere. So this direction vector will also follow over. But yeah, so this also defines a near plane and a far plane, which are going to be the depth values, essentially. The maximum depth and the minimum depth that we want to render with the directional light. So I'll just call it bounding region BR. And then, like I said, we're going to have a GLM mat4, and we're going to call it a light space matrix, and this will just be the transformation to a light space. And that's going to be the projection time, or it's projection times view, I believe. And then we'll have our FBO for the shadows. And we have to include a few things here, actually. So include /algorithm/bounds.h, and then include frame memory.hpp. And then we can have for FBO shadow FBO, or frame buffer objects, sorry. Just like that. And now we're going to have two new methods. One's going to be a constructor, because we want to, when we call the constructor, we want to initialize the FBO so that it's prepared to render stuff. So dirlight, we'll pass in a GLM vec3 direction. We're going to essentially pass in all the values with the bounding region, but not the matrix. So GLM vec3 direction, GLM vec4 ambient, GLM vec4 diffuse, GLM vec4 specular, and then bounding region BR. And then we also want to have a method to update the matrices. So update the light space matrix, actually. It will be return type void, and we'll just call it update matrix, or matrices. God, I can't, my throat is hurting a little bit. I could be infected, you never know. But it's hurting to talk, or not hurting, but I'm not pronouncing my words as clearly, I don't think. Okay, so those are the new methods that I want to have in the directional light structure. We should actually make this a class at some point, just because it's not really a structure anymore. It functions as a class. And then for the now we're going to go and define these methods. So go into light.cpp, and we'll start with the constructor. You can actually just copy the definitions or the signatures over. Make sure to have your tag. And this will essentially, it will initialize all the values that we pass in. So direction goes to direction, ambient goes to ambient, diffuse goes to diffuse, and specular goes to specular. And then also the bounding region BR goes to BR. Now, this isn't just going to be a blank constructor. I should check my temperature. Oh, I'm feeling my forehead. It's like 500 degrees. I'm fucked. This is just... Thank you for the tip, Provin, but I think I'm already... I see the writing on the wall. 500 degrees, that's way too hot. And it's Celsius too, which is even funnier. So I don't even know how I'm alive right now. Okay. Then we also forgot to initialize the shadow FBO. So the shadow FBO, we will call the constructor with width and height. So I'll just pass in 1024 for the width and height, and then the bit combo will only be GL depth buffer bit. You just remember that's the only thing that we want to render here. We don't care about the colors. We only care about the depth of certain objects in the directional light's point of view. All right, now we want to actually initialize the or set up the FBO. So shadow FBO.generate, then shadow FBO.bind. This is going to be very similar to what we have in main.cpp that we did last time right here, or up here actually, where we generate and bind a few things and then load in attachments. So we'll then have shadow FBO dot disable color buffer, because we remember we don't want to write to it, write or read from it. And then we want to allocate a texture. So shadow FBO dot allocate an attach texture. We'll pass in the attach type is GL depth attachment, GL depth component for the format, and the type will be GL float. And then we want to call update matrices too. And this update matrices method will set up the initial space matrix for the light. And we're actually going to define that right now. For update matrix, it's going to be not too different from what we've seen, but it's going to be different, or it's going to be a different way to express a space matrix, but it's going to be relatively the same format. So we're going to have our projection matrix, glm mat for proj is equal to glm ortho. So we're going to, once again, we're going to use an orthographic projection because everything in this directional light is parallel. And orthographic is, we've used it to render text before, and it just essentially has a it assumes it essentially just takes in think about if we had a camera, but the camera only took in light rays that were perpendicular to the screen, or to the lens, and the lens was flat, it wasn't curved or anything to make a cone of view or to focus anything. It would only take in perpendicular arrays. So ortho, we're going to pass in, we're going to use the bounding region to define the range of values that we want to render in the orthographic projection. So we'll have br.min.x, br.max.x, then for the bottom, br.min.y and br.max.y, and then finally for the near and far, it's going to be br.min.z and br.max.z. What this defines is the clip region. Or is it clip region? I forget what it's called, but if an object is not within this region here relative to the light, then it won't be rendered, or it will show up as not being normalized in the multiplication. And then we're going to have a light view matrix. So glm mat4 light view is equal to glm lookat. So we're going to use the lookat function. However, we need to define a position first. And it's going to be glm vec3 pose is going to equal, and you can experiment with a few constants and see what you like. And once again, the constant will relate the direction to the position, and it has to be negative. So the pose will, I'm just going to use negative 2.0 float times direction. And then glm look at will be pose. Look, the eye is at pose. The center is going to be the origin. So glm vec3 0.0 float. And then the up vector will be glm vec3 0.0 float, 1.0 float, and 0.0 float. So this is pretty much what we have with our camera. If we see, if I go to camera.h or .cpp, in camera.update vectors, or is it update vectors or it's get view matrix? We use the look at function once again, except we're just looking at a different origin, where the origin is just the front of the camera. And the projection matrix we calculate in the scene class, in scene.process input, I believe. Yeah, projection is equal to the perspective projection. So we're essentially using the same template to define a camera here, except we're just integrating the camera within the light to simplify things. And then finally, the light space matrix of the directional light is going to equal projection times light view. What's up, Harjot? Is it Harjot? I don't know if it is. I hope it is. Okay, so believe it or not, it's as simple as that. It's just we're essentially just replacing the. Okay, good. I'm not an idiot. It's okay. So yeah, we're just replacing the projection and view matrix with different matrices for the specific view, or for the specific eye in this case, or sun actually. Okay, so now that we have this, we have to create a way to render the scene in the directional light's point of view. And we're going to do that as we have been with shaders, and we can actually just use our scene class as well. And we're going to use our scene class, and we will create a new function called, what's it called? We're going to call it render directional light shader. All right, shader.h. Ooh, no, not shader. Scene.h. So for render shader, what this function does is it takes the values that we have stored in the cameras of the scene. So in get active camera, we have specific cameras, and that we're going to render for the user's point of view. But now we want to have a second method called render directional light shader, and I'll just put it up here. Void render dir light shader, and we'll pass in a shader just like we have. I'll copy this definition or the signature over, and then for the body, it's actually going to be pretty simple here. Let me just find it. We're just going to activate the shader, so shader.activate, and then shader.setMat4, light space matrix, and then dir light dot light space or I need to add this shader tag or this scene tag so it recognizes it as an object. Dir light dot light space matrix. Do I explain OpenGL concepts in depth? If you want like a quick crash course on some conceptual stuff, I would recommend watching the. Yeah, okay. I do. In episode 7 specifically, I talk about VBOs, VAOs, and EBOs. But if you want something a little shorter, I would recommend watching. There's a video. It is the one after video 29 where we kind of recap the stuff, and it's a little shorter, or because it's just a recap, we're not actually doing any code in there. But I do specifically talk about how to I specifically talk about how all three of those connect together. And then also, I believe in episode 23 we create classes for those three things. So those concepts are also explained pretty thoroughly or in depth per se in that video. So 7, 23, and then the recap. Am I going to be making a game? I really want to. I really want to, but there's just so much that I want to do with the engine. Because I mean, I could make a game with this, to be honest. Pretty simple one. Because we have most of the stuff in place that we're doing shadows now. We have physics in place, we have collisions in place, but there are some other things that I do want to look at. But you know, I might actually just do that because I should. Because I'm making a tutorial on doing an engine is fun and stuff. But and not applying it isn't good. So I should actually apply this to a real world situation. But so yeah, I'm thinking of doing a game. How did I learn OpenGL? I learned it on learnopengl.com. I'm not lying. I mean, the first part of this series is pretty much just learnopengl.com with a little butter on top, but it's not plagiarism. It isn't plagiarism. Don't worry. All right, let's avoid. we have avoided this topic, or continuing with the code. But yeah, this is so back to the code. We're in render dir light shader. This is the only thing that we're going to use because if you guys remember, in our really early, in our very basic Vertex Shader, this is from a long time ago, we only cared about a projection and view matrix, and then the model matrix we also multiplied over here, and it's going to be exactly the same. We are essentially going to have a setup that's just like this, except we're doing the multiplication on the CPU side, and it just makes things a little simpler. You could do it either way, but it doesn't matter too much. So that's going to be the only thing that we have to set for the directional light shader on the CPU side. And then so yeah, that's directional light, rendering to the directional light. And let's actually write this shader right now. So I'm going to create a new folder in shaders, call it shadows or just shadows, and then I'll copy and paste. And for the vertex shader, I'm going to call it directional shadow.vs. And then for the fragment shader, since once again we don't care about the color, I'm just going to call it shadow.fs because it can be generalized to all of these lights here. And it actually, we can have an empty main function here. We don't need anything but the macro at the top and the main function. No outputs, no inputs. It doesn't matter at all because we don't need to write to a color, and we actually disabled the write buffer, so this wouldn't be able to write to anything except the depth value. And now for the directional shadow.vs, this is going to be, most of this code is here, but I'll just rewrite it. This is going to be pretty common or pretty standard. So for the layout, I'm using glad. Yeah, that's, once again, that's exactly what this thing told me to do, so I did that. I don't know what the difference, I actually don't know what the difference is. But I could, someone did ask me a question about glue a while ago, and it looked a little different, but I don't know. Yeah, so for the vertex shader, we're going to have 3 layout variables. We need the position of the fragment, so layout location is equal to 0, and this can be in vec3 a pose, and then we're going to have an offset and a size. So layout location is equal to 3, and we're skipping 1 and 2 because in the mesh class, the layout, the variables at location 0 are the position, 1 is the normal vector, 2 is the texture coordinate, and those are all lighting specific, and they only affect the color. They don't affect the position, so we can just discard those, or not discard them, but just ignore them. So layout location 3 is going to be in vec3 a offset, and then layout location is equal to 4 in vec3 a size. And then we also want to take in the uniform matrix, so uniform mat4 light space matrix. And we'll have our main method here. So it's going to be gl underscore position is equal to light space matrix times the vector 4 of a size times a pose plus a offset, and then 1.0. This is directly synonymous to object.vs, where we calculate the model matrix, which is essentially just scaling it and then translating it. And then we multiply it by the light space matrix, but the light space matrix is just the projection times the view matrix specific to the directional light. So we're doing the same process, just broken down into different steps. All right, let me refill my water, and I'll be right back. I will just add a comment in here. Okay, so this is going to take care of rendering the shader, or rendering the scene, in the directional light. And let's actually go into main.cpp and finish this up. So we're gonna have some errors here. I'm actually gonna delete a few things in main.cpp because we don't need them. So the FBO that we have, we don't need. That was just for demonstrations last time. We don't need the plane, but you could use the plane actually to render the, or you know, let's actually do that. So this directional light, we have to now call the constructor. So we'll call the constructor, pass in the 4 values, the 4 vectors, and then the bounding region. Pass in a GLM vec3, and we'll say negative 20.0 float, negative 20.0 float, and then the near plane, or the near pane, will be 0.5 float. And then the second vector will be GLM vec3, 20.0 float, 20.0 float, and you can experiment with the far plane. But it essentially just defines how far away the shadows will reach. And we can say 20, and we'll see how this affects it. And that should... Oh, one more parenthesis. Alright, so this constructor here will set up the FBO, so we actually need to move this above the plane generation, because if we want to access the texture, we're going to have to say map.init with dir_light.shadowFBO.textures at 0, because it's the only texture that we generate here. And then what else did I want to do? There's going to be a few other errors. FBO.activate, you can clear that. I'm actually going to get rid of the, you know, let's take care of the rendering, and then I'll remove a few things. Okay. Yep. So once again we want to render the default frame buffer and then render the plane to the default frame buffer. And then before this, we now want to actually activate, instead of the custom frame buffer that we had before, we want to activate the directional lights FBO. So dir_light.shadowFBO.activate, and then everything we render from now on will be rendered like this. And then to actually to show the depth values, since we only have the depth values, we need to go back to buffer.fs, and instead of rendering to a color map, we want to render the depth values. And I believe there was a different way that we wanted to do this. Yeah, okay. So because it's an orthographic projection, we can't actually use the depth map here. So this is depth map perspective. So we have to comment this out too. Because remember, it's orthographic. So we're going to have depth map. This time it's orthographic. And the code will be just frag color is equal to a vector 4 of the vector 3 of the texture, and we're going to call we're going to change the name of the texture, but it will be dir_light.depthBuffer, and the coordinate will be text coord as before, and we're only going to get the R value, and then we convert that to a vector 3, and then we just add put a 1.0 for the fourth component. So now to change the component here, we're going to have the structure, and we'll just say struct dir light. And since we don't need any of the other light values, we can just pass in the sampler 2D depth buffer and mat for light, or just the depth buffer actually. And then we'll have a uniform dir light, dir light. Alright, so that's the depth map orthographic. And then before we actually run this and see what the scene looks like from the directional light's point of view, we actually have to create a new shader here, because we want to render it using the light space, remember. So we'll have shader light, or dir light shader, and the vertex shader will be the directional shadow.vs. So assets slash shaders slash shadow slash directional shadow.vs, and then the fragment shader will be assets slash shaders slash shadows slash shadow.fs. And then we have to use this shader actually to render stuff. So we'll call scene.render shader on the directional light shader, but we have that other method, so we have to say scene.render dir light shader and pass in the dir light shader. And then we can actually just get rid of a lot of this stuff here. So I'm going to get rid of the outline because we don't care about that anymore. I'm also going to get rid of all the lamps because I don't want to confuse stuff right now. So I'm actually just going to get rid of the lamps, and then also the spotlight. So let me just comment out all of this code here. So I'm commenting out all of the spotlight and point light code. And this should give us an error. Yep, it does. Oh, that was from before. I think we should be good. Are we good? We can also comment out the lamp model, just because we don't need it. Alright, so let's run this and see if it works. I hope it does. Don't know if it will. 60% confidence. Ooh, alright. Must write to GL position. Did I not? Oh, directional shadow. I passed in the wrong path. Alright. 70% confidence. 0% confidence. That's bullshit. Shit. Let me move the default frame buffer binding to right before the loop starts, because that might be a problem. Alright, let's run this again. Still, alright, 50% con. Yeah, fuck it. Let me get rid of this outline there. So we activate the directional light FBO, and we render the stuff using it. Render the spheres and the cubes, and then we activate the FBO, the default FBO, and render the map. That should be good enough. Unless... Let me see what is... Let me try setting the color to... Oh wait, this could be wrong. Yeah, in buffer.fs, let me try setting the color to just 0, or just black. See if it's actually rendering this to make sure. Okay, so I think the texture is working, but let me check something. Alright, dirlight.shadowfbo.activate, scene.render dirlight shader, then render the scene. And then we activate the default FBO and render the map. I think that's all working, it's just not getting this stuff. Alright, let me make sure that the process that it goes through over here is right. So I'll have a breakpoint in light.cpp in the constructor. So we'll run this. Okay, BR is right. Because I was getting errors with the bounding region before, but I think it's looking good. Now this .br, yep, that's also good. Alright, so let me make sure that this is all good. Okay, generate, bind, disable color buffer, which disables both the draw and read buffer. Then allocate and attach texture, depth attachment, depth component GL float, and then we call update matrices. Here, this. Looking good. -2 times direction. That's fine. Light view. Projection times light view. Okay. Let me try playing around with the bounding region here. Let me make this like 50. Okay, I think I might know the problem. This is a little weak, this strength here. So I actually had changed it in here to make it -0.2, 0.9, and -0.2. And then I also increased the strength of the and then I increase the strength of the diffuse and specular, so this should become 0.6. And then 6, and then 7 for the specular. Alright, let's run this. Damn it. I mean, I feel like I can see something, but my eyes are definitely playing tricks on me. Let me just respond to a text real quick. That looks all white. I'm not gonna, just to me. But that means it's not seeing any of the objects. Which means, oh, I'm rendering it with the wrong fucking shader, of course. Yeah, okay. We're rendering the spheres and the cubes with the shader, with the default shader, but we should be rendering it with the directional light shader because that renders it to the shadows FBO. So now let's run this, and it should be better. Voila, there we go. So that's what the directional light sees in oh, this was great transition. Let me turn this up a little. So yeah, that's what the directional light will see when we render it, or when we render the scene from it. And then that's the depth buffer that we will be using to calculate the shadows now. Okay. So to actually get from the directional light's FBO to the default FBO, or am I from? I'm not telling you that. That's too much information. Bro, I'm fucking scared of what people can do online. You give them one piece of information. Putting my name out there is honestly risky enough, but I can use this on a resume now. That's all this is, just something to put on the resume. That's a lie. I hope you guys know that, but you know, people are scary online. Anyway, so now that we want to actually go from the directional light's point of view to just the default point of view, we have to consider how to get the FBO and to the depth buffer to the regular shader. And there's a reason why I put the FBO within the directional light structure. It's because this is just a texture. We can just pass it in as a texture. It's okay. Fuck, I don't know why that's so funny, but it's okay. God damn it. Yeah, so we're just gonna pass in a texture here, and all we have to do is in light.cpp, in directional light.render, we're just gonna pass in both the buffer and the texture index, and the texture and then the matrix as well, because we need to transform it. So we actually have to add a parameter here to render, and then will be an unsigned integer texture IDX. If you remember in mesh.cpp, if I have that open, I don't. To render stuff, we give texture slots. There's texture units in the GPU, and we need to tell it which texture unit to use. So we'll just pass that in. We'll control that from the scene class, so we can just pass that in up here. So where is it? Light.cpp, and we will pass in a texture index to the render method. Let's put that over here too. So set depth texture. So we have to activate the texture slot. This is just the same procedure. GL active texture, GL texture 0 plus texture index. Then shadow FBO dot textures at 0 dot bind, and then we need to set the integer. So shader dot set int dir light dot depth buffer. We're going to add this into the structure in a second, and then just texture IDX. And then we want to send in the light matrix, which is pretty self-explanatory. Shader dot set mat4 dir light dot light space matrix, and then we pass in light space matrix, like so. Now in scene.cpp, we have to figure out what index to pass in. And because with the mesh we're starting from 0 and we're counting up, the temporary solution, before I figure out technically what you should do here, or find a better way, is we're going to count down from the maximum slot, which on most computers happens to be GL texture 31. So I'll start with the index. So in scene.cpp, render shader, we're going to have an unsigned integer texture IDX, which is going to equal 31. And then when we pass this into DirLight, we're going to say pass in shader, and then texture IDX minus minus. And I'm just doing minus minus because if we were to put another light below this, I'll just put this actually before the other two lights. But when we actually pass in values here to the point lights and the spotlights, we're going to pass in texture indices as well. So I'm just going to subtract one here so it's updated for the next one, so we're not overwriting textures. So that's on the CPU side, or yeah, that's on the CPU side. Let me just make sure I got everything. Scene.cpp. Okay, let's go to object.fs now, and we will incorporate this now. Ooh, let me turn this up. Okay. For the directional light, we have two new values here. So in the structure, just add a sampler 2D for the texture. It's going to be depth buffer. And then a mat for light space matrix. And these should directly correspond to the names that you gave it in scene.cpp, or not in scene.cpp, in light.cpp. These ones right here. Okay. Alright, so I'm going to have a new method here. It's going to return a float, and it will be called calc DirLight shadow. Takes in no parameters. That's the signature, and then I will copy that, paste it over here. And then in the actual function, we're gonna return either a 0 or a 1. 1, it's just because it's Boolean. If it's in the shadow, it's gonna be a 1. If it's not, it's gonna be a 0. And what we're gonna do with this is, in calculate DirLight, we're gonna get the shadow value. So float shadow is equal to calc DirLight shadow. And then this is only going to affect the diffuse and specular. So even if it's in the shadow, we still want to have some ambience in it. So we're going to have a 1.0 minus shadow times, then in parentheses, diffuse plus specular. So calculate DirLight should return a vector 4 of ambient plus a 1.0 minus shadow, that in parentheses, and then times, and then in another set of parentheses, diffuse plus specular. Now for the actual calculating the shadow, this is going to be fun. We're first going to get the fragment position in the light space. So vec4 frag pose light space is equal to DirLight dot light space matrix times the vector 4 of frag pose and 1.0. You might be wondering, well, isn't the fragment position the position in the camera's point of view? Well, if you remember in object.vs or instancing or instance.vs, the fragment position is only affected by the model matrix. GL position, the final output of the vertex shader for all our objects, takes into account the projection and view matrix for the camera. And we then output the fragment position, which is the world coordinates, to the fragment shader. And it wouldn't make sense to pass in the projection coordinates because we don't want to render light from the camera. Yeah, we don't want to render light from the camera's point of view. It would complicate things infinitely. This just makes it a lot easier to just handle where the fragment is in the world. So that's the fragment position in the light space. Then we want to perform what's called a perspective divide. And this is going to be transforming the coordinates to normalized device coordinates. And all it's going to be is just vec3 projection chords is equal to frag pose light space dot xyz divided by frag pose light space dot w. What this does is it translates it from near far to -1 1. This original range I don't think is right. Or wait, no, it's just the depth relative to the light. Yeah, this is just the depth relative to the light. So it could be negative, it could be whatever, but it's just -1 to 1. Ooh, you know what that means? You know, I'm gonna save my thought for. Give me. I'm gonna save it for a second. Then we're gonna go from the normalized device coordinates to depth range, and this is. You should be seeing some similarities here to the buffer.fs where we're transforming between normalized device coordinates, or transforming to normalized device coordinates, and to and from. So now we're going normalized device coordinates to depth range, which is just so proj chords is equal to projection coordinates times 0.5 plus 0.5, and this is just going to be -1 1 2 0 1. That's the new range now. So what I'm thinking now is that since everything is going to be translated to a 0 to 1, that means that objects behind the light will be rendered for shadow calculations. So it doesn't fucking matter. I'm sorry for my language, but it doesn't matter where the position is as long as it's along the direction vector. So especially with the directional light, it doesn't matter if we set the position to just the direction vector, because it can be an object can be all the way out in buttfuck Vietnam. It can be all the way in Timbuktu. It could even be in the Pacific Islands for all I care. But it would still render it if the position was a certain value, because it's behind it. As long as it's in, the only thing that truly matters is the x and y. So where we set, where is it? These values here, the br.min.x, br.max.x, and then same thing for y. These are the only things that matter, because if those are not normalized, then it won't render it at all. Or if those are not within the normalized range, then it won't render it. Okay, so now we have it in depth range. Now we want to get the closest depth. This is just going to be float closest depth is going to equal the texture value, so we're just taking it straight from the texture. Duralight dot depth buffer, and then proj chords dot xy, since it's just 2D, and then we're just going to get the red value, which is just the depth value. And then we want to get the depth of the component, or of the fragment. So that's float current depth, and that's just going to be projection coordinates dot z, just because when we render or transform it to the light space, the z coordinate becomes how far away it is, and we normalize that. And then what we can say is if the depth is greater than, it's going to be closer. Then return 1. Or sorry, if the depth is greater than, it's going to be further away. So return 1. Otherwise return 0. So return current depth is greater than closest depth. Question mark 1.0 colon 0.0. The reason why we're doing greater and we want to determine if it's further is because, once again, we have the 1.0 minus shadow. And the reason why we have a 1.0 here is because it wouldn't make sense to return a 0 for a shadow if that meant it was in the shadow. You could say we could return a light constant here and then just multiply that light constant by the diffuse plus specular. Alright, see ya. Fuck, I'm not even gonna, I'm sorry, I'm not gonna attempt to pronounce your name. I don't want to axe that. That is, yeah, well, we'll have a good one. So yeah, we have a 1.0 minus shadow, so it's going to make sense to return a 1 if it's in shadow, 0 if it's not. Okay, so that's yeah, that's pretty much all of what we need to do outside of the main file. Let me actually just or no, we're okay to continue. So now back in the main function, since we want to render the scene twice, it's going to be easier to have a function just to render everything, because we're going to be rendering the same objects from the camera and from the directional light. So it doesn't make sense to just copy the code over and over again. So we can just have a function here that takes in a shader and it will render the scene. So at the top of main.cpp, we're going to have a function signature called void render scene, and we'll pass in a shader. And then I also wanted to make the objects global here, just so we have access to them in this function here. So the sphere and the cube should be made global variables in the main file. And now for the actual function itself, we're going to go down below and paste it in. And then what we can do here is now take the code that we used to render only the instances. So all the code here. So if sphere.current number of instances is greater than 0 to render the cube, just cut that and paste it in the render scene function, and then just replace the Light shader with the shader. So this function will assume that the shader has already been pre-rendered or prepared accordingly. So let's then render this using the function. So render scene, pass in Light shader. So we're not going to see shadows right now. I just want to take a screenshot of the buffer so we can kind of compare it. All right, so this is our buffer. And we're doing this. Where'd it go? Here we go. All right, so I'll leave that right there. All right, now we're going to, this is where you should get your rags or your tissues out, just because this is going to be climactic. We're going to set up the scene to be rendered properly, or the regular shader. So scene.render shader, or we actually have to, one thing, we have to reactivate the default VBO. So render scene normally This one up here was rendering the scene for the directional light. So to render the scene normally, we're going to say scene.defaultfbo.activate, then scene.renderShader, just a normal method here, pass in the shader, and then render scene shader. And I think we're almost there. Oh, and then we need to remove where we rendered the texture. Don't forget to remove that. Okay, I'm prepared for this. Oh, it's right. It's fucking right. Yeah, it looks like dog shit. Trust me, I know it. This looks like absolute shit. Oh fuck, I just screwed it up. Press the volume button. But there's an explanation for this. This is expected. We're gonna fix this next time, but the basic stuff is there. So we should see, according to, oh, this is why I put the epilepsy warning in the description. This is fucked up for if you like. This is just, all right, where's the image? So we see 2 blocks on top of the plane, and how many shadows do we see on the plane? Where is it? We see 2 shadows on the plane, so that corresponds perfectly. And if we go high up, we'll see that there's one block here that doesn't have the crisscross pattern on it. So there's no shadows on top here. And this may be either, I'm thinking this is, I actually can't tell which is which. But where's the other block? Is it this one? Oh, I think it is this one. But this looks weird as fuck. I don't know what this is, but what the hell is? Yeah, this shape is weird, but so this. Okay, I actually don't know which is which. Or wait, no, those 2 wouldn't be casting shadows. I think it's gonna be. If we're looking at the directional light, it'll probably be. Actually, where is the directional light? I'm seeing specular from here. It's probably... Alright, so it's probably like over here or something. There's a shadow on there. I can't really tell. This was supposed to help me determine where blocks actually were. So it might be like that. That actually looks right, yeah. So this block here casts this shadow, maybe. And then this one casts this shadow. Now, should we try... I might want to try launching a ball. And see what happens. Alright, ready? Did it work? I don't know if it worked. Let me try changing the let me change the size here. Yeah. Okay. Oh, yeah, I saw the shadow. Look at that. Did you guys see the shadow? God, I'm so fucking happy. Oh, that looks like shit. But you see the shadow though, and it's moving. Let me make this a little smaller, like 0.5. But the shadow is there. Yep, there it is. Fuck yeah. That's how it's done. Damn. Yeah, you'll love to see it. That's pretty cool. Is this Moog City? Fuck, I just ruined it again. But yeah, so that's pretty much shadows. I mean, there's this dumbass pattern on here, but we'll fix that next time. That is actually not an error. It is, fuck, I keep touching the volume buttons. But that's just a consequence of what was it? Of a lot of these errors here. So you can kind of see the pixelation, or it looks like it's super pixelated, like right here. And this is just simply a consequence of our texture having a finite resolution. If it were to have an infinite resolution, it would be perfectly blended. And we'll figure out how to fix these two things next time. And that will be in like 2 weeks, unfortunately, because I'm going to be visiting family for the holidays. But however, I will be working on OpenGL code. I will be going hard, nuts to butts. I will be drinking Mountain Dew at 3 in the morning, working on OpenGL code, and I will ram out like 5, or not 5, but a few OpenGL videos when I get back. Where am I? Why am I inside the cube? But yeah, there's a lot to come here. There's a lot to fix with this, definitely, because it looks like shit, but it's just stuff to look forward to. So yeah, this was actually really fun to do. I was super fucking satisfied when this worked, when I was testing it. I almost punched a hole through the wall, and I may or may not have yelled a few profanities in the process, but it worked, and that's all that matters. So yeah, next time we're going to be working on optimizing this, and then beyond that we'll be applying this to the spotlight and point light, which will be different and similar in certain ways. But yeah, that's pretty much it for me. Hope you guys enjoyed. Hope you learned something, especially learned something. And if you have any questions, leave them in the comments. I hope I can answer them. But yeah, enjoy yourselves. This will be happy holidays. I hope this year ends quickly, but you never know. We could have World War III within 3 days of 2021 starting, and we'll just have a repeat. But I'm not going to get political. I'm pretty much done here. So yeah, I'll see you when I'm back from vacation, and we'll get right back on the grind. So until then, have a good one and enjoy yourselves.
Three,